Hi, my name is Katrin and I'm going to present our work, Sign Segmentation, with change-point modulated pseudolabeling. This work was done in collaboration with Nico, Neil, Gil, and Samuel. For temporal sign language segmentation, we want to predict the time of the transition between two signs in a continuous sign language video. For this, we assign each frame either to the sign or the boundary class. Here the blue bars correspond to the boundaries between the signs. But why do we want to do this? One big challenge for the development of automatic recognition and translation systems is the lack of large annotated sign language datasets. This is driven by a limited supply of annotators and the extremely high cost of producing the labels. Here you can see an example for the approximate annotation time for 1 hour of sign language video. With an automatic segmentation system, we could speed up the annotation process and therefore create larger datasets. Recent work tackled this by training a model on a dataset where fine-grained annotations are available and transferred this trained model to different datasets without any fine-tuning. The model consists of an I3D backbone for the extraction of spatio-temporal features and a multi-stage temporal convolutional network for the segmentation. The transfer leads to a lower performance in the main metric MF1B. In this work, we want to tackle this problem. Besides the standard challenges of sign language segmentation, such as motion blur or occlusion, we deal with extra challenges stemming from the domain transfer. Here you can see example images of the 3 datasets we used. On the left, the source data, and on the right, the unlabeled target data. It is clearly visible that background, signers, and their pose differ. In addition, we use data of different languages. On the top, British Sign Language, and on the bottom, German Sign Language. We consider the hypothetical case where a model is trained on a labeled source dataset which is not publicly available. This can be the case to maintain the privacy of individuals or if there are no rights to make the dataset public. Since in the domain of sign language, the group sizes which can contribute to a dataset are smaller, personal identification is easier. This can put the contributing individuals at higher risk, also as the audiological status is sensitive information. We now have a second dataset, the target data, without any labels. Therefore, we can't train the same model from scratch and want to make use of the pre-trained model. We fine-tune the model to reduce the impact of the domain gap. To improve the performance on unlabeled target data, we propose the change-point modulated pseudolabeling method. We use the pre-trained model from the previous work to extract pseudolabels. Here in dark blue, you can see the pre-trained I3D and MSTCN models. In these pseudolabels, we encountered a subtle but systematic bias towards undersegmenting signs. We used the assumption that there are particular gestural movements that correlate with sign boundaries and corresponds to human motion disfluencies as well as changes in the sign discriminative feature space. We integrate this knowledge into the pseudolabeling process and combine the pseudolabels with change point detection, which detects the changes in feature space. With these combined labels, we then fine-tune the MSTCN model. There are several ways to combine the pseudolabels and the change points. A first intuitive one is to take the union of both sets and merge the labels. This leads to broad boundaries when the predictions are not aligned. A second option is to take only those regions of pseudolabels into account where over a long time no boundaries are predicted. To do so, we calculate the average length of a sign in the whole dataset and insert change points only in regions longer than this average length. The last option is the change point modulated pseudolabeling algorithm, which consists of 2 stages. First, the insertion step. For each boundary in the change point detection, we look at the close neighborhood in the pseudolabels. If there is already a boundary, we do not insert a new boundary. In this case, there is no boundary, so we can insert the change points. Note that the distance of the neighborhood area is set as a hyperparameter and is just an example in this visualization. After the insertion step, we refine boundaries at locations where in both sets a boundary is predicted. This is to minimize the bias towards a different annotation style in the source data. We match the closest boundaries and change the locations to the mean position. We present several ablations. Here you can see the results of the presented fusion techniques. Our CMPL algorithm leads to the best performance. Training with only pseudolabels or change points already gives an improvement. We also present the impact of the two stages of the CMPL algorithm. Using only the insertion step, we obtain a significant boost in performance in our main metric MF1B. But the combination of both steps provides an even better result. Here are some qualitative results. The first line is the ground truth. SO, or source only, is the previous work which transfers the model without any fine-tuning. Then we have the training only on pseudolabels and only with change points. And the last row is our CMPL method. Especially in the green region, our model is able to detect previously undetected boundaries. The video is slowed down by a factor of 6. Here you can see some of the limitation of this technique on a different sequence. We can counteract the under-segmentation problem by inserting change points. By doing this, we also get slightly more false positives, as you can see here on the left. Since we only insert and refine existing boundaries, the model is often not able to suppress boundaries which were already wrong in the pre-trained model. This happens mostly for abrupt direction changes in the middle of one sign or between a repeated sign. Thank you for your attention.